Okay, my wonderful students. Unfortunately, my microphone is actually this microphone's working, but my earbuds are not working again today. So, but this will record off the internal microphone of my computer. Um, let's talk about exam X. We don't have the Scantron scores back yet. Unfortunately, they'll probably be in tomorrow. Usually it's hard to predict. It's supposed to take 2 days, but sometimes it's a little bit longer. So I'll try to post those results over the weekend, and then on Tuesday in lecture, what I'll do and what Tricia and I will do is hand back the exam printout that comes from the test scoring service. And what it will do is show you the exam questions that you got right and which ones you got wrong. And then I'll publish a little outline for each item on the test form A, B, C, and D, a little blurb about what each question was, except for the matching. That's kind of hard to do, but for the multiple choice and true false and stuff, you have a little blurb, like it might be about eccentricity. So I might have a little, like 2-3 word blurb about what that question is about. And that way you'll be able to look at the printout and then the list of blurbs and figure out, okay, I better for the final exam, I better concentrate on eccentricity and ellipsis, or I better concentrate on Newton's law of universal gravitation, or whatever you find is your trouble area. All right, so we'll have those on Tuesday for you, hopefully, and we'll just take the first 10 minutes or so of class, and we'll come down to the floor here, and I'll take from A through L, and Tricia will take from M through Z, last names, and we'll just hand them out person by person. And it'll take a few minutes, but then you'll have it, and it'll work good. Okay. Any questions from you about the exam? Okay, let's keep going. We'll probably talk a little bit more about the exam on Tuesday. We're going to start working on the planets in the solar system. And I really like this figure. This is figure 2 from chapter 7.1. I like it because it helps you see the relationship between the 8 standard planets, Mercury through Uranus and Neptune, and then the other ones, including Pluto, which is now declassified to dwarf planet. And you can see that they've kind of drawn it with a little bit of depth, a little bit of perspective, so that you can see that, like, the Eris object in the Kuiper belt is on a kind of a tilted orbit. And Pluto is actually, you can see that Pluto is tilted as well. And a lot of the dwarf planets out there are fairly tilted. Now, if you look at the inner solar system, you'll see Ceres, C-E-R-E-S. Now, that's the biggest asteroid, okay? And it's pretty big, and it's got kind of a tilted orbit. Matter of fact, the planets are all tilted relative to each other, but not by much. And you can see that in this diagram. They're all, plus or minus a few degrees of being perfectly flat. But the comets and stuff out in the Kuiper belt, not so much. I want to go over this particular screen grab. This is from chapter 7, Other Worlds. And it's just a little list of the mass as a percentage of the total solar system for each object in the solar system. So Sun, Jupiter, comets, all other planets and dwarf planets, moons and rings, asteroids, cosmic dust. And that's an estimate. And comets and asteroids are estimates because it's hard to see all of them. We don't know that we've got all of them. So we're kind of making an estimate on that. And what I want you to look at and see from this is from chapter 7. It's a table. It doesn't have a number or anything, but it's right at the beginning of chapter 7. 99.8% of the mass, the number of kilograms in our solar system, is in the sun itself. And 0.1%, 0.10, a tenth of a percent, is in Jupiter. And then look, all the other planets, 0.04%. That includes Saturn. Saturn's a pretty good sized planet. And that includes us, 0.04, all the other planets. It seems pretty big. Earth seems pretty big to us. It's rocky, lots of silicon dioxide in our planet. And the core is iron and nickel. But it's a pretty shrimpy little fraction of the solar system in terms of mass and in terms of size. Here's a close-up of it. So what I want to dwell on with you and think about is this figure here, the sun, 99.8% of the mass of the solar system. All right. And we're going to compare that to Jupiter. Get your clicker ready, because we're going to do a clicker question here. And we got a few more clicker questions today. So, yeah, Jupiter, 0.10%. So that's kind of shrimpy compared to the sun. I mean, you know, you can just see it. Now, those are percentages of the total mass of the solar system. All right, now I want to look at it in a slightly different way, and that's with this clicker question. So go ahead and turn on your clicker, frequency DD. And here's question number 1. The masses of the sun and Jupiter are 99.80% and 0.10% of the solar system. All right, now those two masses make a ratio. What ratio would it be? A, B, C, or D? Let me turn on the question. So this is multiple choice. Okay, you can start answering your question. Let's see what you guys got here. And this is just kind of a mental exercise. You know, all right, as a fraction of the sum, yes, but in terms of each other, you know, what is their mass ratio? Okay, 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That's good, 182 people here and voting. Yeah, most of you chose A, that is correct. And if you didn't do that, it's just move the decimal point for Sun 1 point to the right, and for Jupiter 1 point to the right, and then it'll be 998 to 1. Now, my point here is that's roughly a ratio of 1,000 to 1. Another way that you could put it, and this is not in the slide, that's Jupiter is just about 1 part per 1,000. Did you ever hear that? You know, people talking about like the purity of water or the amount of contaminant in water or some solution, you know, so many parts per 1,000, you know, a concentration. Well, this is about 1 part per 1,000. One Jupiter is worth 1 part per 1,000 in the entire solar system scheme of things, pretty close to it. All right, now here's the visual comparison. Right, so make a note of this sketch. This is a 1,000-liter water tank. And you know, you can see all kinds of pictures of 1,000-liter tanks on the internets, But it's kind of hard to see one that allows you to see actually how big it is. There's nothing to scale. It's just, a picture of a tank with a blank background. There's no, I searched for about 10 minutes before I found this one. Some kind of a car. Looks like I don't know, it's like an SUV or something there. But that's 1,000 liters of water. And every liter is worth 1 kilogram of mass. So that's actually 1 metric ton of water. Now, see this little job here? Get my cursor over here. There's a liter bottle. I tried to shrink it down to about the right size. A liter bottle of smart water. So that's like Jupiter. And then the big tank is like the sun, for the scale. So it shows you, that another visual way to show you that ratio, 998 to 1. It's almost 1,000 to 1. So you're going to have, I'm going to try to dismiss early today, if that's all right. And see if I can go talk to the guys that are grading the Scantrons, which is in this building, actually. So let me just point out that you're going to have some reading homework this weekend. This is figure 2 in section 7.3. And if you look at it carefully, you'll see over there on the horizontal axis the number of half-lives. And if you read 7.3, in which this is figure 2, you'll see that it's talking about radioactivity and isotopes, and how we use radioactivity to measure the age and the composition, and sometimes the origin of different rocks and objects that we find in the universe. And we actually use it in astronomy. Now, here's another eye clicker question for you, and this one's probably tough. Let me preface this. How many protons are there in a regular hydrogen atom? Just one, right? And how many electrons? Just one. Okay. Are there any neutrons in a regular hydrogen atom? Nah. All right, so hydrogen is 1 proton, 1 electron most of the time. All right, now, here's a little slice of the periodic table, and this shows you oxygen. So the question is, in a molecule of H2O, 2 hydrogens, 1 oxygen, how many protons are there? Okay, and let me start this question. Okay. Go ahead with that. And just think, H2O, 2 hydrogens, and then but 1 oxygen, so that, a different number of protons there. And you can read, if you remember your periodic table, you can, and I'll remind you after this question, if you remember your periodic table basic ideas, you can figure out how many protons are in a regular oxygen atom from the periodic table. All right. 30 seconds. And let me remind you that, exam 4 is going to be here before you know it. Exam 3 is going to be here before you know it. Jot this question down along with the answer, little mini study question. And sometimes I basically take a clicker question, I rephrase it maybe a little bit, and put it on a midterm. So, so this is good to study with. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Wow, good. 195 people voted. 196. Sweet. All right, let's see what you guys have got here. Most of you voted correctly. If you didn't vote correctly, the periodic table tells you the bottom number, especially if it's close to a whole number, tells you the number of protons and neutrons in the nucleus added together. Okay, so for hydrogen, it's 16. The top number, excuse me, for oxygen, it's 16. So 16 neutrons and protons, and then the top number, 8, tells you how many protons. So the bottom number tells you how many protons and neutrons. The top one says how many protons, so you got 8 and 8. 8 protons, 8 neutrons. However, if you look at chlorine, look at the bottom number. That's the mass number for chlorine. What is it, 35.45? The reason for that is that there are variations in chlorine and other atoms, and those variations are called isotopes. Now I'm going to give you a little instruction on this before we dismiss. Isotopes, here's the spelling of it. Isotope. And basically, an isotope is a variation in the nucleus of a given element. Okay, hydrogen has isotopes, oxygen has isotopes, uranium has, most of the elements we've seen different isotopes. And they tell us a huge amount of information. Now, in this is what we call isotopic notation. The mass number is up on the top, and the atomic number is in the subscript. Okay, and the chemical symbol, of course, is the capital letter H in this case. All right, now we're going to work and talk about some other isotopes in which the mass number is going to be, like for uranium, 238, 235. For oxygen, that would be 16 in the oxygens that we just talked about. But there are other oxygens that have 17 and 18 for the mass number. All right, so let's talk about isotopes. It's basically an atom with some extra what we consider to be extra neutrons in the nucleus. And the best way to understand it is with hydrogen. So it might be extra or maybe a few missing neutrons or fewer neutrons. And so for hydrogen, let's compare it to hydrogen. Regular hydrogen is 1 proton and 1 electron orbiting. And that is 99.9885% of all the hydrogen that we see. Now, we can test it. Basically, we check the mass of hydrogen atoms, and we find that 99.9885% of all of them are like that, a proton and an electron. Now, if we filter them out, we can find isotopes. And this first isotope is called deuterium. And it is basically, it's still a hydrogen because it only has 1 proton. It has 1 electron in its neutral state. But it does have a neutron, and the neutron is bound to the proton in the nucleus. All right? And that forms a fairly small fraction of all hydrogens in nature. So when you drink a glass of water, you're drinking in a few of these, not too many. Right? You can filter it out of regular water. 0.0115% of all hydrogens are actually deuteriums. And this is what we call heavy water. It usually gets the symbol D. And if you're near a nuclear reactor is going to produce deuteriums from regular hydrogen. Okay, because a nuclear reactor is going to have a lot of neutrons flying around. That's what causes the reaction. All right, and if you're moderating your nuclear reactor with some water, some of the water is going to form deuterium. The neutron that's flying around doing the nuclear reaction with uranium, some of them will be captured by the nucleus of a regular hydrogen atom, and it'll become a deuterium atom. And so, if you've ever heard the term heavy water, like In terms of nuclear weapons, uh, there's a current controversy concerning Iran and their effort to acquire nuclear weapons. And some of their atomic reactors are what we call heavy water reactors. Okay, and there's reasons to use heavy water reactors. Uh, in World War II, the United States and Britain targeted a famous hydroelectric plant in Norway that had taken regular water off the glaciers of Norway, and going through a big hydroelectric dam to make electricity. And one of the guys there had made a point of filtering out the deuterium hydrogens. And so they had a lot of heavy waters, and the Germans were trying to get it. In fact, the Germans invaded Norway and they conquered Norway. They didn't bother with Sweden, they just wanted that heavy water so that they could have a nuclear weapon. And they didn't succeed, partially because the British and the Americans destroyed that hydroelectric plant in a series of raids. You can read about them and even see movies about it. There's been several movies about the raid on the Norsk hydro dam up there in Norway, and it was all about heavy water. Now there's a third isotope of hydrogen. This is another one with extra neutrons, all right, and that's called tritium. Tritium. Deuterium is from the Greek word deuter, which means two. Tritium is three. Three items in the nucleus. This one is really unstable, and my wonderful students, it is also extremely rare. It is made in nuclear reactors, the same process, neutron capture, and then filtered out. And tritium is actually used in nuclear weapons. Right now, the current controversy is the North Koreans trying to develop what we call a hydrogen bomb. And a hydrogen bomb either uses, well, it can use regular hydrogen or deuterium or tritium as the fuel for the chain reaction that becomes an explosive detonation, an extremely powerful one at that. So tritium is another isotope of hydrogen. And it's radioactive. It's very unstable. That means we would call it radioactive. It glows in the dark. They use it to paint devices that have to glow in the dark reliably, but it's extremely expensive. And if you want to get attention from the FBI, just say the word, "Oh, I have some tritium," on your phone, and they'll be outside your house in about 30 seconds. No, hopefully not. But anyways, it's not something normal civilians are going to have access to, but it is an isotope. Now, I want to give you a side note about how we separate them. And a lot of the devices that we used in World War II, the Manhattan Project, used a centrifuge. And here's a picture of it down here. It basically emits some, in this case, uranium. And the heavy uranium curves on a bigger arc, and the lighter uranium isotope cuts a little bit tighter of a corner. And that's how they separated it. Another one is called gaseous diffusion. And again, this one it's not a centrifuge. Matter of fact, the centrifuge is what is one of the controversies over in Iran right now. Do they have the capability of making a centrifuge to purify uranium isotopes? Because only uranium-235 will work with for an atomic weapon. The electromagnetic separation was called the calutron in Oak Ridge in the Manhattan Project. They had another one out in They had a big gaseous diffusion plant out in Washington State up by the Columbia River, way out in the middle of nowhere. And there's other methods of separating isotopes. In each method, the isotopes, they separate because they have a different mass. So that's like, you're in the grocery store, you have an empty grocery cart and a loaded grocery cart. They're going to you give each of them the same size push, they're going to behave differently. One of them's go a little farther. All right. Now, it's not quite that easy with isotopes of uranium, but if you put them in a magnetic field, they'll curve around like that because they're charged, and then they'll behave differently. Now, here's a picture of the plant called Y12 up in Oak Ridge, Tennessee, and it's in this valley. This is during its construction during World War II. 60 years ago, we would not be permitted to see this photograph. It's because if you study this, if the Russians had seen this photograph, they could figure out exactly what they were doing at Oak Ridge. I mean, to us, it just looks like a building, right? But if you study it, you can figure out what it's doing. So here's basically what they're doing. There's a little website, osti.gov. So the uranium chloride, it comes out as an ion. It's a charged particle. You put it in a magnetic field, and the light ones will turn a tight curve, and those are the ones you want, uranium-235, 92 protons, and a bunch of neutrons. And then the one that you do not want, uranium-238, that kind of curves around a little bit further of an arc, and actually, uranium-238 is the stuff that they make into, now they use it for making ultra high density ammunition that can destroy, one or two shots of depleted uranium, they call it, will destroy a tank, most tanks. So depleted uranium rounds. If you ever hear of that, in the Air Force or the Army, they've got them. I don't think the Navy uses depleted uranium. Maybe they do. But anyways, that's where it comes from. That's the U-238. But for the nuclear weapon, it's U-235. And because that's the isotope that will undergo the catastrophic chain reaction. U-238, you can make it undergo a reaction, but it won't provide as much energy per atom as U-235. All right, so let's get back to what is an isotope. What is an isotope? All elements have isotopes. Some of them are stable. Now, this is the one that we're going to concentrate on, oxygen. And actually, hydrogen isotopes are pretty important too. Oxygen has 3 stable ones: oxygen 16, oxygen 17, and oxygen 18. And we think that oxygen is manufactured inside the core of stars when they're kind of middle-aged and they're getting really hot, and they start to fuse heliums into carbon, nitrogen, and oxygen. And some of the some of the oxygen is 16s. Some has 8 and 9. 8 protons, 9 neutrons, that's an oxygen 17. And some has 8 protons, 10 neutrons, that's oxygen 18. Some of the some of the isotopes of oxygen decay radioactively, and other elements as well. And those are the ones that we use to compute the age of something. Now, radium decays very rapidly in minutes and days, and you can look up what we call the half-life. The half-life is a word, it's the word half, H-A-L-F, and then life. And I don't know who invented it, but it's the amount of time, on average, that a radioactive substance will decay away half of its mass. And it's the same no matter if you have a kilogram or a gram or anything in between. The half-life for radium is pretty short. Now, a few thousand years, carbon. The radioactive isotopes of carbon will decay over the time scale of a few thousand years, and these are what we use for carbon dating things on the archaeological time scale. So when we want to go back, 2,000 years to the time of the ancient Romans and those cats, or 4,000 years to the time of King David in Israel, or the Babylonians over there in Babylon and stuff, we would use carbon. You find somebody's campfire and you do some carbon dating and you can find out, sometimes within about 50 years of, the actual date. So it's pretty reliable. Another one is uranium to lead. Uranium will decay into lead on a time scale of 1 billion years. And we actually use this to date rocks, especially rocks from the moon. We can tell that the relative age by counting how many uraniums in a piece of rock of a certain isotope and how many lead isotopes in the same piece of rock. And that ratio will tell us roughly how old it is. Right? So age and location can be deduced from checking maybe parts per million or ratios of the different isotopes. So you can, you get a sample of water, you can check the oxygen isotopes. You get a rock, you can check the uranium and lead isotopes. And there are other radioactive isotopes that we use for geology. If you find a campfire or the remains of it in a cave up in Tennessee, and you want to find out, well, was it from the Revolutionary War or was it from 900 AD or was it 9000 BC? Near the time of the ice ages. You would use check the carbon isotopes, and you get an idea. All right, so you check parts per million or parts per billion. You check the ratios and stuff, and then you make your decisions. Now, you may be asking yourself, Dr. B, this is really, really interesting. I love it. It's nice. But why is there a picture of a beautiful beach? Is this just to torture me, especially in a day? Is it still raining out when you get? It's really nasty out there. I'd really like to be at this place and just kind of soaking up some rays and dipping my toes in the water. But no, it's got to be raining. Write down this word, SMOW. 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 It is a abbreviation, an acronym for Standard Mean Ocean Water in the Oceans of Earth. Standard Mean Ocean Water, SMOW, is basically scientists around the world have sampled water, all over the oceans. They dunk a bucket in the ocean, or they, dunk a bottle all the way down to the briny deep, and they bring up some water from, the Mariana Trench, or the middle of the Atlantic, or the deepest part of the Indian Ocean, wherever they want. And roughly, or the mean value of various isotopes of hydrogen and oxygen are approximately 2005.20 parts per million for oxygen 18 to oxygen 16. So that's the oxygen 18 ratio. And in the ocean, the waters of the oceans of Earth, it comes, so if you analyze a gallon, you're going to come up with about 2005.2, plus or minus a little bit, but it's about 0.20050%. Right? So that's we can measure that. We can hack that. Take your bucket of water into the lab. You put it through a calutron, basically. You separate the oxygens, and then you count them. How many grams have you got? and it comes in at about 2005 ppm. Oxygen 17, that's the other stable isotope. On the ocean, in the oceans of Earth, it comes in at a little bit lower. It's a little bit more rare, 379.9 parts per million. All right, and so that's about 0.03799%. All right, now that's the other. So we can find that. We take a bucket of water, we'll find, every million oxygen 16s, you're going to find 379.9 or 380, I guess, oxygen. Excuse me. For every million oxygen 16s, you're going to find about 380 oxygen 17s and 2,000 of oxygen 18. So that's basically the ratio or the abundances in the oceans of Earth. Now, what we do is use that as a standard, because we don't only study the oceans of Earth. We study things that come to Earth like meteorites and moon rocks. We can even look at comet spectra. We can look at the spectra and see small changes in the oxygen spectral lines. And we haven't looked at those yet, but you can look them up. And there's small changes depending on which isotope of oxygen. And because that's the case, we can actually detect that, things on the Earth and the Moon, the relative abundance is going to fall into a specific pattern. So if you, on this particular diagram, the vertical axis is something called delta 17. That's related to the oxygen 17 ratio. And then the horizontal axis is delta 18. That's related to the oxygen 18 ratio. And delta means how far are you away from SMOW? Okay, so you take something like what we call a chondrule type of meteorite, and you measure the oxygen ratios, and you'll see that it's out of the terrestrial pattern. So the moon and the moon and Earth, all the data falls on this line up here. But then when you look at some certain classes of asteroids, as we're going to do in the next week or two, you'll find that the oxygen ratios are a little bit out of whack. All right, we shouldn't say out of whack. We should say they're out of the norm. They're a little different than what we see in the ocean water of Earth. And then here's another one, CAI. That's a certain kind of calcium inclusion with a certain kind of calcium inclusion in meteorites, and those ones are even further down here. And so on this diagram, negative numbers mean that it's depleted, and a positive number here means it's got more oxygen 17 than SMOW. And down here on the left, a minus number means that it's got less oxygen 18 than SMOW. And I'll show you how to calculate these ratios probably next week. Anyway, so let's, so here's the upshot. Some meteorites show similar oxygen ratios to Earth, but not all of them. Not all the meteorites, not all the comets, not all. And sometimes we'll find unusual moon rocks. Even sometimes we'll find stuff unusual on Earth. And by the way, a few years ago, we sent a spacecraft out into space. It's called the Stardust mission. And they flew the spacecraft through the tail of a comet. It was conveniently nearby us. And they collected dust, particles of dust from the tail of that comet. And they brought it back to, they parachuted it back to Earth. They maneuvered the spacecraft back to Earth, and they parachuted that down. And and they studied just not even grams, just microscopic amounts of stardust. And guess what they found? They found a grain of dust in the tail of the comet that was made in another star, a red giant star somewhere many, many light years away from us. A real piece of another star, because we know it's not from our solar system. It's out of our isotope ratio range. A real piece of stardust. I'll show you that next week as well. So let's dismiss now, and there'll be a reading homework for number 5. I'll look for that tomorrow around lunchtime, and I'll see you next week. So this is early dismissal. Okay, good. And I'll be up here for a few minutes if you want to come and talk to me about anything.